All right, welcome back. So mic check here. Looks good. So let me continue on with the agents course. Now, I am still gonna read the book. The book is
All right,
awesome,
welcome back. So I think
but this agents course has a bit of a deadline. The next unit's going to be released at some point fairly soon. So I definitely want to get this done before that next unit is released. So if we look at the welcome, we should see the calendar for when these next. Yeah, so here's the recommended pace. So today is the 15th. So this is actually going to. So the bonus unit is actually going to be released in on Monday. So I'm pretty far behind. So I think this is the right one to work on so I can meet this recommended pace. Otherwise, I'll be behind the recommended pace. All right, and these are really kind of in-depth and comprehensive too. So following behind is actually quite consequential because there's a lot here. All right, but moving on, understanding AI agents through the thought, action, observation cycle. So we finished step one. We understand what agents are. We finished step two. We learned what LLMs and message systems are. We finished step three, studied tools and actions. So now we're moving on to step four, learning the agent workflow. In the previous sections, we learned how tools are made available to the agent in the system prompt, how agents are systems that can reason, plan, and interact with their environment. In this section, we'll explore the complete AI agent workflow, a cycle we defined as thought, action, observation. And then we'll dive deeper on each of these steps. The core components. Agents work in a continuous cycle of thinking, thought, acting, and observing. Let's break down these actions together. Number one, thought. The LLM part of the agent decides what the next step should be. Number two, action. The agent takes an action by calling the tools with the associated arguments. Number three, observation. The model reflects on the response from the tool. The thought, action, observation cycle. The three components work together in a continuous loop. To use an analogy from programming, the agent uses a while loop. The loop continues until the objective of the agent has been fulfilled. Visually, it looks like this. So make this bigger. So the LLM thought process. So query, think, action, observe. So there we go. Now we're at the think. So we'll move on to an action. It'll observe the results of the action. It'll think and then finish or another. It'll ask itself whether this solved it. So it'll think about that, or it'll end it if it's clear that the objective was complete. In many AI frameworks, the rules and guidelines are embedded directly into the system prompt, ensuring that every cycle adheres to a defined logic. In a simplified version, our system prompt may look like this. So, system message, you are helpful AI designed to help users efficiently and accurately. Your primary goal is to provide helpful, precise, and clear responses. You have access to the following tools: tool name calculator, and remember that this can be automatically parsed by the way we write the code. So when we write this tool calculator that it has, we give it the tool in a Python function. We can decorate that function with another function that calls a class that automatically takes the tool name, the description from the tool docstring, and the arguments from the type checking part of the function if you include that. Back when I first learned Python, type checking wasn't even a feature of Python yet, so I kind of don't consistently use type checking, but As things evolve, staying up to date is a good thing. So uh, type checking isn't too difficult. You just look it up and figure out how to do it. It's just basically making it so that uh, it's part of documenting the function. It makes it more clear what arguments, what data type the arguments are supposed to get, and then it also makes it clear what data type the function returns if it returns anything. If it doesn't, then you would say outputs none type. So you should think step by step in order to fulfill the objective with a reasoning uh, divided in I think this should say derived, reasoning derived. I don't know this word DEVIDED. Maybe it's a new vocabulary word for me. No, it's a misspelling. So it's either derived or divided. In thought, action, observation, it's probably divided. Reasoning divided in how I would write this is you should think step by step in order to fulfill the objective with a reasoning process of thought, action, observation that can repeat multiple times if needed. That's how I would write it. You should first reflect with the your thoughts on the current situation, and then, if necessary, call a tool with the proper JSON formatting. So action, JSON blob, or um, your print your final answer starting with the prefix final answer. Here we see here that in the system message we defined the agent's behavior, the tools our agent has access to, as we described in the previous section, the thought, action, observation cycle that we bake into the LLM instructions. Let's take a small example to understand the process before going deeper into each step of the process. Alfred, the weather agent. We create Alfred, the weather agent. A user asks Alfred, what's the weather like today in New York? So, what's the weather like today in New York, Alfred? Alfred's job is to answer this query using a weather API tool. Here's how the cycle unfolds. Thought, internal reasoning. Upon receiving the query, Alfred's internal dialogue might be, the user needs current weather information for New York. I have access to a tool that fetches the weather data. First, I need to call the weather API to get up-to-date details. This step shows the agent breaking the problem into steps, first gathering the necessary data. So here's the think step. The user needs current weather information for New York. I have access to a tool that fetches weather data. First, I need to call the weather API to get up-to-date details. All right, so then the action would be tool usage. Based on its reasoning and the fact that Alfred knows about a get weather tool, Alfred prepares a JSON formatted command that calls the weather API tool. For example, its first action could be thought. I need to check the current weather for New York. So the action could be get weather, which is a function, and then the what you could provide the function is the location on New York. So here the action clearly specifies what tool to call. For example, get weather, and what parameter to pass the location New York. And remember, this is all based on an LLM, right? So it's like, using logits and probabilities and all that. So if you name your tool something like, you know, a period, underscore weather tool, I think it probably wouldn't do as well because it's that next character would probably not be. So I think you need to name these so that it's more likely to select them. Hopefully, there'll be more information about that later on, but that's something to consider, I think. Especially if it's not selecting the tools. If it's just like ignoring one of its tools, it might be because of how the tool is named. So here the action clearly specifies which tool to call. For example, get weather and what parameter to pass. The location, New York. So this is the act step. Action get weather, action input, location New York, weather API. Observation, feedback from the environment. After the tool call, Alfred receives an observation. This might be the raw weather data from the API, such as current weather in New York, partly cloudy, 15 degrees Celsius, 60% humidity. So current weather in New York is partly cloudy, 15 degrees Celsius, 60% humidity. So that's the observation step. Now, if it came back current weather in Chicago and it was asked to fetch the weather in New York, there should be some check in this observation step for it to be able to observe that it did not complete the objective. This observation is then added to the prompt as additional context. It functions as real-world feedback, confirming whether the action succeeded and providing the needed details. Updated thought. Reflecting. With the observation in mind, Alfred updates its internal reasoning. Now that I have the weather data for New York, I can compile an answer for the user. So this is the think step. Final action. Alfred then generates a final response formatted as we told it to. Thought. We have the weather data now. The current weather in New York is partly cloudy with a temperature of 15 degrees Celsius and 60% humidity. Final answer. The current weather in New York is partly cloudy with a temperature of 15 degrees Celsius and 60% humidity. This final action sends the answer back to the user, closing the loop. So there we go. Now the user is very happy and is a member of Hugging Face. What we see in this example, agents iterate through a loop until the objective is fulfilled. Alfred's process is cyclical. It starts with a thought, then acts by calling a tool, and finally observes the outcome. If the observation had indicated an error or incomplete data, Alfred could have re-entered the cycle to correct its approach. Tool integration. The ability to call a tool like a weather API enables Alfred to go beyond static knowledge and retrieve real-time data, an essential aspect of many AI agents. Dynamic adaptation. Each cycle allows the agent to incorporate fresh information, observations, into its reasoning thought, ensuring that the final answer is well informed and accurate. This example showcases the core concept behind the React cycle, a concept we're going to develop in the next section. The interplay of thought, action, and observation empowers AI agents to solve complex tasks iteratively. By understanding and applying these principles, you can design agents that not only reason about their tasks, but also effectively utilize external tools to complete them, all while continuously refining their output based on environmental feedback. Now let's dive deeper into the thought, action, observation as individual steps of the process. So thought, internal reasoning, and the React approach is next. All right, and this is a pretty short session. I'll pause it and be right back. All right, welcome back. So this next part is thought, internal reasoning, and React approach. In this section, we dive into the inner workings of an AI agent, its ability to reason and plan. We'll explore how the agent leverages its internal dialogue to analyze information, break down complex problems into manageable steps, and decide what action to take next. Additionally, we introduce the React approach, a prompting technique that encourages the model to think step by step before acting. Thoughts represent the agent's internal reasoning and planning processes to solve the task. This utilizes the agent's large language model, LLM, capability to analyze information when presented in its prompt. Think of it as the agent's internal dialogue, where it considers the task at hand and strategizes its approach. The agent's thoughts are responsible for assessing current observations and decide what the next actions should be. Through this process, the agent can break down complex problems into smaller, more manageable steps, reflect on past experiences, and continuously adjust its plans based on new information. Here are some common examples. So here's some examples of common thoughts. So type of thought. So we've got planning. I need to break this task into 3 steps. Number 1, gather data. Number 2, analyze trends. And number 3, generate report. Analysis. Based on the error message, the issue appears to be with the database connection parameters. 3, decision making. Given the user's budget constraints, I should recommend the mid-tier option. Problem solving. To optimize this code, I should first profile it to identify bottlenecks. Memory integration. The user mentioned their preference for Python earlier, so I'll provide examples in Python. Self-reflection. My last approach didn't work well. I should try a different strategy. Goal setting. To complete this task, I need to first establish the acceptance criteria. Prioritization. The security vulnerability should be addressed before adding new features. Note, in the case of LLMs fine-tuned for function calling, the thought process is optional. In case you're not familiar with the function calling, there will be more details in the actions section. The React approach. A key method is the React approach, which is the concatenation of reasoning, think, with acting, act. React is a simple prompting technique that appends let's think step by step before letting the LLM decide the next tokens. Indeed, prompting a model to think step by step encourages the decoding process toward next tokens that generate a plan rather than a final solution, since the model is encouraged to decompose the problem into subtasks. This allows the model to consider sub-steps in more detail, which in general leads to less errors than trying to generate the final solution directly. So, the D is an example of React approach when we prompt let's think step by step. So I don't know what they mean by D. So we've got 4 different prompts here. We've got one that is a few shot prompt. So the question is, Roger has tennis balls, has 5 tennis balls. He buys 2 more cans of tennis balls. Each can has 3 tennis balls. How many tennis balls does he have now? So the answer is 11. So this is a few shots. So you're giving it, and it's an alternative to a 0 shot. So a 0 shot would be you just give it one question, same question, well, similar question. A juggler can juggle 16 balls, which is not true. The most a juggler can juggle is 13. Half the balls are golf balls, and half are the golf balls are blue. I think it's 13. It could be 12. Yeah, it's not 13 because in order to juggle, you need to do twice the number of objects. That's the minimum definition of what it means to juggle. So so Alex Barron here, one of the best numbers jugglers in the world, is not juggling 13. He is attempting to. So he's attempting to get. Um, well, he is juggling, but it it depends on your definition. Um, so it's the answer is 11. The most number of objects ever juggled is 11 because they've gotten 22 or more catches. 12 world record is the world record for 12 individual is um, so that's group juggling passing it is only 20. So it'd have to be 24 for 12 to be the most highest number of objects ever juggled in quotes. So we can see, this is kind of a big goal right now in juggling to get that 12 catch mark, because then that would mean that no longer is it the case that 11 is the highest number of objects ever juggled. Now 12 would be the highest number of objects ever juggled and documented throughout human history. So you can see lots of our best number jugglers in the world are working on this. So he just needed to do two more throws, and he would have made it so that the highest amount of objects that has ever been juggled before in human history in a way that is documented and verifiable would be 12 instead of 11. So I just wanted to point that out because juggling is my main hobby, and I've met, I've had dinner with Tom Whitfield. I haven't met Alex Barron, but like, these, like, I know what it means to juggle these kinds of numbers. Like these people they do everything right. Like they practice, they're in shape. Like they use the right kinds of balls, they use the right kind of training methods, and just like in other areas of their life, they're similarly just like amazing. So like I you know, but the answer is 11. So the highest number of so the world record for 11 is 34, but I think for quite a while, quite a number of years, 22 catches of 11 ball has been achieved. So that there is the world record. It's 3 cycles, so it's been juggled for 1.5 cycles, for more than 1.5 cycles. One catch more than 1.5 cycles. But this is what it means to juggle. It means twice the number of catches as objects, and that there is a video of the most number of objects ever juggled in a documented and verifiable way throughout all of human history for the most number of catches. All right. So, and just as an aside, the restaurant we went to was plant-based vegan. So a little bit of if anyone's wondering about that, like, yeah, like that's kind of a secret when it comes to high-level performance like that. All right. So, anyways, zero shot. A juggler can juggle 16 balls. Half of the balls are golf balls and half of the balls are blue. How many blues? So the answer is, and you didn't even give a example of the answer, not even one example. So this is a zero shot prompt, so it's not likely to get it right. Yeah, so we can see the difference in the prompts. A few shot gives it one example before it asks for the real question. So we can see the real question is in black here, and then the few shot example is in green. But we can see all it did was give the answer. So a few shot example with chain of thought reasoning, COT, We can see in green here the few shot example, but now we can see the answer is more comprehensive. It includes it shows its work. And now we have a zero shot yeah, so there we go. And let's think step by step. That's a key prompting phrase. We have already seen a lot of interest for reasoning strategies. This is what's behind models like DeepSeek R1 or OpenAI's O1, which have been fine-tuned to think before answering. These models have been trained to always include specific thinking sections enclosed between think and think special tokens. This is not just a prompting technique like React, but a training method where the model learns to generate these sections after analyzing thousands of examples that show what we expect it to do. Now that we understand the thought process, let's go deeper on the second part of the process, act. So actions enabling the agent to engage with its environment. In this section, we'll explore the concrete steps an AI agent takes to interact with its environment. We'll cover how actions are represented using JSON or code, um, the importance of the stop and parse approach, and introduce different types of agents. Actions are the concrete steps an agent takes to interact with its environment. Whether it's browsing the web for information or controlling a physical device, each action is a deliberate operation executed by the agent. For example, an agent assisting with customer service might retrieve customer data, offer support articles, or transfer issues to a human representative. Types of agent actions. There are multiple types of agents that take actions differently. Types of agent. JSON agent. The action to take is specified in JSON format. Code agent. The agent writes a block of code that is interpreted externally. Function calling agent. It is a subcategory of the JSON agent, which has been fine-tuned to generate a new message for each action. Actions themselves can serve many purposes. Types of action. Information gathering, performing web searches, querying databases, or retrieving documents. Tool usage, making API calls, running calculations, and executing code. Environment interaction, manipulating digital interfaces or controlling physical devices. Communication, engaging with users via chat or collaborating with other agents. One crucial part of an agent is the ability to stop generating new tokens uh, when an action is complete. And that is true for all formats of agent, JSON, code, or function calling. This prevents unintended output and ensures the agent's response is clear and precise. And not only that, if you're using one of the products, like the API product from OpenAI, if you're deciding to buy rather than build, um, and you don't have reliable stop actions for your agents, you're just going to have one agent who's just to check the clock, to keep checking the clock continuously and bankrupt your whole company. So you have to. This is probably one of the most important parts of agents, especially if you're choosing to buy rather than build. But in either case, it's very important. The LLM only handles text and uses it to describe the action it wants to take and the parameters to supply the tool. The stop and parse approach. One key method for implementing actions is the stop and parse approach. This method ensures that the agent's output is structured and predictable. Number one, generation in a structured format. The agent outputs its intended action in a clear, predetermined format, JSON or code. And I'll do a mic check. Perfect. Halting further generation is number two in the stop and parse approach. It's a three-step approach. Once the action is complete, the agent stops generating additional tokens. This prevents extra or erroneous output. Number three, parsing the output. An external parser reads the formatted action, determines which tool to call, and extracts the required parameters. For example, an agent needing to check the weather might output, thought, I need to check the current weather for New York. Action, action get weather. Action input, location, New York. The framework can then easily parse the name of the function to call and the arguments to apply. This clear machine-readable format minimizes errors and enables external tools to accurately process the agent's command. Note, function calling agents operate similarly by structuring each action so that a designated function is invoked with the correct arguments. We'll dive deeper into those types of agents in a future unit. Code agents. An alternative approach is using code agents. The idea is instead of outputting a simple JSON object, a code agent generates an executable code block, typically in a high-level language like Python. So let's take a closer look at this. This is a very busy graphic. So instruction, determine the most cost-effective country to purchase the smartphone model, Code Act 1. The countries to consider are the USA, Japan, Germany, and India. So available APIs. Number one, lookup rates API. Number two, convert and tax API. Number three, estimate final price. Four, lookup phone price. Five, estimate shipping costs. So these are all things that you would write. All right, so the LLM agent using text/JSON as action, I should calculate the phone price in USD for each country, then find the most cost-effective country. So the action would be lookup rates. We can see that's one of its available APIs or tools. JSON tool lookup rates for the country Germany. So it's going to look it up for Germany. And now these are the environment. So we get 1.1, 0.19, which is interesting. I'm not sure what that means. Okay, so this is what happens if you use if the LLM agent using code as action. But now we can do code act, whatever that is, and we can have fewer actions required. So with code act, now it can use code in this action. So now instead of having to use a new for each thing it wants to do, going through it, now it can just do it by writing out code. So it can make a list of all the countries and then do a for loop through those lists and do it all in one action, rather than having to do an action for each of the countries in the list. So it's good that it can use control and data flow in its code to simplify complex operations. And it can also reuse the mint function from existing software architectures, the Python library. Doesn't have to do this. Yeah, so you definitely want it to be doing its actions in a way that empowers it to use code. This approach offers several advantages. Expressiveness. Code can naturally represent complex logic, including loops, conditionals, and nested functions, providing greater flexibility than JSON. Modularity and reusability. Generated code can include functions and modules that are reusable across different actions or tasks. Enhanced debuggability. With a well-defined programming syntax, code errors are often easier to detect and correct. Direct integration. Code agents can integrate easily with external libraries and APIs, enabling more complex operations such as data processing or real-time decision making. For example, a code agent tasked with fetching the weather might generate the following Python snippet. Okay, so this would be what we see here, but for fetching the weather. So it would so code agent example, retrieve weather information. So def get weather city, so to import a request, it would you give it uh, the URL, and you'd have to provide your key here in plain text. But you can yeah, there's ways not to have plain text here, but you have to figure that out. Then it plugs in the input it was given to the function here for the correct city. So this input has to be given correctly. Um, then it will give you back the response. So if the response code is 200, that means it was successful, so it can return the data. Otherwise, there was some kind of error, so it was unable to fetch the data. In the example, the code agent retrieves weather data via an API call, processes the response, and uses the print function to output a final answer. This method also follows the stop and parse approach by clearly delimiting the code block and signaling when execution is complete, here by printing the final answer. We learned that actions bridge an agent's internal reasoning and its real-world interactions by executing clear structured tasks, whether through JSON code or function calls. This deliberate execution ensures that each action is precise, um, and ready for external processing via the loop stop and parse approach. In the next section, we will explore observations to see how agents capture and integrate feedback from their environments. After this, we will finally be ready to build our first agent. Hooray, that'll be interesting. So, and it looks like this. You can update it on GitHub. Um, so, yeah, so uh, I could make an edit. Now I'd have to fork it, and then return it. So I could do that for the typo that I saw earlier. I think it wasn't. It was on the prior page, but you know what? Forget about it. It wasn't a big deal. So the next section would be observe integrating feedback to reflect and adapt. And before I get ahead of myself here, let's go to ChatGPT and open these last ones that I read, and then we'll go to operator, and then we'll say I want you to create high quality Anki cards for me to study uh, for me to study. I am. So I want you to create high quality Anki cards for me to study. Okay. So here is a checklist of objectives. Number one, research what makes the most effective Anki routine and cards. Number two, uh, one by one, create cards for the following material. Okay. Number three, add all necessary cards to learn the material to Anki Web. I will likely need to sign you into Anki web at this point. Number 4, function completely autonomously, making all of your own choices based on the results of your research for what is most effective. All right, that should be good. So now it's so it's going to research how to make good Anki cards. It's going to go through what I've read so far, and then go to Anki Web and create a deck that I'll be able to pull down here in my local instance. And we can see last time I used it, it did that as well. It did it. It made its own deck for the for this cycle here, but that was just kind of experimental. All right, so I need a break. I'll be right back. All right, I'm back. I'm typically good for an hour, so I've got about 20 minutes here to go. So look at this. This is so cool. So I prepared a card about, oh, I'm still logged in too from a prior thing. Yes. Continue adding cards. There is no need to verify with me first. Wow, this is really cool. I mean, there's value in making your own cards. So, you can't just take its word for it yet. I mean, at some point, the model will know everything there is to know about psychology. It'll do its own research on psychology, and it'll just like, man, what a world we're entering. Well, anyways, moving on. Okay, so the last one was actions enabling the agent to engage with its environment. So this next one will be observations. So observe, integrating feedback to reflect and adapt. Observations are how an agent perceives the consequences of its actions. They provide crucial information that fuels the agent's thought process and guides future actions. They are signals from the environment, whether it's data from an API, error messages, or system logs that guide the next cycle of thought. In the observation phase, the agent collects feedback, receives data or confirmation that its action was successful or not, appends results, integrates the new information into its existing context, effectively updating its memory, adapts its strategy, uses this updated context to refine subsequent thoughts and actions. For example, if a weather API returns the data partly cloudy, 15 degrees Celsius, 60% humidity, this observation is appended to the agent's memory at the end of the prompt. The agent then uses it to decide whether additional information is needed or if it's ready to provide a final answer. This iterative incorporation of feedback ensures the agent remains dynamically aligned with its goals, constantly learning and adjusting based on real-world outcomes. These observations can take many forms, from reading web page text to monitoring a robot arm's position. This can seem like tool logs that provide textual feedback of the action execution. So we've got different types of observations. I'll just make sure this is still going. Okay. All right, so that is done. So now I can go into my Anki pin here, and it will automatically sync down the changes. So now we've got the new cards here. It made 7 new cards. So let's study them now. So what are the components of the thought, action, observation cycle in AI agents? Let's take a look. So the thought is when the agent plans its next action based on its goals and current context. Action is the agent executes The plan action and observation, the agent receives feedback from the environment, which informs. Yeah, these are not very high quality card. What's the purpose of the React approach? React approach aims to make agents more effective in real world tasks by combining reasoning and action. Allows agents to think before acting, ensuring that their actions are purposeful and aligned with their goals. That one's pretty good. What are JSON agents in the context of AI agents? JSON agents are a type of AI agent that output their actions in a structured JSON format. This format is easy to parse and interpret, allowing for clear communication between the agent and external tools or systems. That one's pretty good too. Well, it's not, because I already know what JSON is, so it's kind of self-evident in the question. Not a good one. What are code agents in the context of AI agents? Code agents are a type of, oh, this is a good one. So code agents are a type of AI agent that output their actions as executable code, typically in high-level programming language like Python. This allows for complex logic and direct integration with external libraries and APIs. What is the stop and parse approach? In the context of AI agents, the stop and parse approach is the method used by AI agents to clearly define the end of an action and the beginning of an observation. It ensures that actions are executed in a controlled manner and the resulting observations are accurately captured and integrated into the agent's context. What is the role of observations? Oh, this is a repeat card, I think. What are the different types of operations? System feedback. Oh, this is a good card too. System feedback, data changes, environmental data, response analysis, and time-based events. What are the components? So these are just going through. I'll just mark them all as good. I'm not doing a serious study session here, so. Um, all right, so yeah, so here's the different kinds of observations. So the first one is system feedback, error messages, success notifications, status codes, data changes, database updates, system file modifications, state changes, environmental data, sensor readings, system metrics, resource usage, response analysis, API responses, query results, computation outputs, time-based events, deadlines reached, scheduled tasks completed. So you can see just how valuable this would be when it comes to network engineering. Like all of this stuff is really valuable, these kinds of observations, throughout all kinds of different fields. So how are the results appended? After performing an action, the framework follows these steps in order. Number one, parse the action to identify the functions to call and the arguments to use. Number two, execute the action. Number three, append the result as an observation. We've now learned the agent's thought action observation cycle. If some aspects see still if some aspects seem a bit blurry, don't worry, we'll revisit and deepen these concepts in future units. Now it's time to put your knowledge into practice by coding your very first agent. So I'm not sure if we had observations included in the operator task, but let's add that. So hopefully there's a history. Ah, there is right here. Okay, cool. So we can go back and check if this was in there. Nope, observations was missing. Okay, good. Now make cards and add them for this learning material. There's no need to. There's no need to verify anything with me until you are finished. All right, so there we go. Now it's gonna, so it's got the observations. Oops, did it include observations? I didn't tell it to do observations. I told it to do agent steps and structure, thoughts and actions, but not observations. So if it did, then see, now it's doing the dummy agent library. I don't know why it's doing that. Yeah, it's not doing what I said. It's doing the next one. Well, anyway, it doesn't really matter. So the next one is oh, and you know what? I'm almost done with this. So I will close this out even if it takes more than the hour. And then I'll be ahead of when the next one's released, and I can focus entirely on the book. So dummy agent library. So we finished studying the agent cycle. Now we're going to create my first agent. So this course is framework agnostic because we want to focus on the concepts of AI agents and avoid getting bogged down in the specifics of a particular framework. Also, we want students to be able to use the concepts they learn in this course in their own projects using any framework they like. Therefore, for this Unit 1, we will be using a dummy agent library and a simple serverless API to access our LLM engine. You probably won't use these in production, but they will serve as a good starting point for understanding how agents work. After this section, you'll be ready to create a simple agent using small agents. And in the following units, we will also use other agent libraries like LangGraph, LangChain, and Llama Index. To keep things simple, we will use a simple Python function as a tool and agent. We will use built-in Python packages like datetime and OS so you can try it out in any environment. You can follow the process in this notebook, and run the code yourself. Okay, so we can just click here, open it in Google Colab, and run it ourselves. Serverless API. In the Hugging Face ecosystem, there is a convenient feature called Serverless API that allows you to easily run inference on many models. There's no installation or deployment required. So let's should be in the notebook. So run this cell, run anyway. Okay, so we should get to this point. So as seen in the LLM section, if we just do decoding, the model will only stop when it predicts the EOS token. And this does not happen here because this is a conversational chat model, and we didn't apply the chat template it expects. If we now add the special tokens related to the Llama 3.2 3B instruct model that we're using, the behavior changes and it now produces the expected EOS. So that's the first big pitfall is you got to make sure you're using the right uh, special tokens for your model. There's no standardization across models, not even for like one version of Llama to the next. So you have to make sure that you're looking those up and using the correct one. And the good thing is, Hugging Face makes it easy. They give you a special tool to look up the special characters. Um, so they had it in the training material, but I think it's probably somewhere else as well. Um, so maybe it's in the documentation. Oh, the documentation doesn't work. Well, anyway, the easy way is I have it bookmarked under Career Hugging Face Essential Tools, so the model formatting visualizer can will show you them. All right. So, so there we go. Using the chat method is a much more convenient and reliable way to apply uh, chat templates. The chat method is recommended to use in order to ensure a smooth transition between models. Since this notebook is only educational, we will keep using the text generation method to understand the details. Okay, so it looks like this is going to be duplicate text. Um, Yeah, so this is the same text that's here. Let's do this in the notebook so we can actually run the cells. So next we're going to run it here. So in the Hugging Face ecosystem, there's a convenient feature. Yep, so as we read about. So to run this, you'll need to get a token. So we need to paste my token in here. Set it up under settings, secrets, and then we'll call it HF token. So we'll do that. And I'll do that off the camera, so I'm not just giving my token out to the world. So I have to go under settings. Notebook settings. Oh, that's not it. Oh, here it is, secrets. So I'll pause it and make sure I have that correct. All right, I'm back. So I generated a new token, a new secret, and I added it to the secrets. We can see the secrets is now in blue. Oh, that's because it's been selected. So I unselected it, and I should be able to go on now with this one. So I'll run that one again. Oh, and you know what? I need to. Yeah, so I can uncomment this line. I think. Is my keyboard working? Yes, it is. Okay, so I can uncomment this line, and then. Oh, you know what? I think. Okay, it should be fine. So as soon as the LLM section does not have secret access, grant access. Okay, there we go. So now this client.text generation knows that it needs to get the secret. Ah, there we go. So now it worked. Yeah, it worked. So as seen in the LLM section, if we just do decoding, okay, produces that. So now we add the special tokens. There we go. Now we get Paris. Using the chat model is more convenient, reliable way. Okay, Paris. The chat method is the recommended method to use in order to ensure a smooth transition between models. But since this notebook is only educational, we'll keep using the text generation method to understand the details. So next section is dummy agent. In the previous sections, we saw that the core of an agent library is to append information in the system prompt. This system prompt is a bit more complex than the one we saw earlier, but it already contains information about the tools, cycle instructions, thought, action, observations. So this is the system prompt. It's a bit more complex. So there we go. Okay, since we are running the text generation method, we need to add the right special tokens for our model. So we got them here. This is equivalent to the following code that happens inside the chat model. Yep, so, okay. So the prompt is now, let's print out the prompt. There we go. So let's decode. Do I see the problem? I do not see the problem. All right, so the problem was the answer was hallucinated by the model. We need to stop to actually execute the function. So, oh, we need to pause so that it actually has the ability to use the function rather than barreling forward without using it and hallucinating an answer. So we can see it should have been clear to see the problem because the answer should have been a hallucination. Yeah, so it got it wrong. So we can actually what's cool about this is we can change it. Like forget about London, right? Let's see what it's like in Austin, Texas. There we go. So now it's more easy to see that it hallucinated, right? Because it says it's a high of 78 and a low mostly sunny. I can look out my window. No, it is not mostly sunny, and I doubt those are accurate. So let's take a look at the Austin, Texas weather. So the high today is 72, the low is 38. It's a cloudy day, and the wind is 11. So it got every aspect of that wrong. It completely hallucinated it. The high is wrong, the low is wrong, and the breeze is less than half as strong. There's not going to be a gentle breeze today. There's going to be more of a brisker breeze. So now I see the problem because I can look out my window to verify whether or not it hallucinated. But so we need to stop it. So we're going to add that stop there. There we go. Much better. Now let's create. So there we go. Now it's going to stop. So now let's create the dummy get weather function. The in real situation you would call an API. Yeah. So instead of just yeah. So oops. But let's change this to Austin. Okay, and we could see, yeah. So in a real situation, we would call an API. We could do that. Weather API, free weather API. Oh yeah, yeah. Uh, okay, so we're gonna give it to GPT. Oh, I'm not logged in. Okay, now I'm logged in. So rewrite the code in the screenshot to utilize the following weather API. Okay, and then we'll uh, take a look at the code that we're interested in, which is here. Okay. All right. Hopefully it will do good on that. So operator is still making cards for me. All right, to give it some time on that. So let's concatenate the base prompt and completion until function execution and result of the function as an observation, and resume the generation. Okay, so we'll run this cell next. Oops, and I forgot to change this from London to Austin, so we'll do that because I want to see based on does it match what I see outside my window. And it looks like my keyboard stopped working, which is annoying. Need to figure out why it's doing that. Okay. Uh, all right. So New York, where did that come from? Right. That's weird. Why is New York in there? Well, it's because we're giving it a few shot example for in the prompt, which is good. You want it to do that, and we should see think step by step. That should be part of the prompt as well. Uh, I don't see that in the prompt. All right, so it's so see what the answer is here. The weather in Austin is sunny with low temperatures. That's because we haven't swapped out this code yet. That gives it that load, puts ammo in the gun, right? Like all we have is this here. That's going to return a static answer. So once we get the yeah, so let's get the actual code. So get yeah, so now we've got the actual get weather. So we can just plop that in here. There you go. Run that. Cool. So there we go. 14 degrees Celsius with a wind speed of that. Um, rewrite it for re okay, thanks. Now rewrite it for someone to read who is from the USA. Use Fahrenheit and miles rather than Celsius and kilometers. All right. Okay, so it's still thinking here. I don't know why it's taking so long now. Uh, maybe the call's gonna fail. Cell is already running, but it's doing a poor job of running. Uh, okay. Well, that's annoying. You know what it does? Oh, okay. Now, oh, runtime disconnected. So I think there was let me try one more time. Oh, you know what? It did it. It did it. Let me try it one more time. There. Now it actually worked, and we can see it matches the weather report here. Well, it's closer. It doesn't exactly match it. Yeah, 58.3. That doesn't exactly match it. Wind speed is way different as well. Ah, well, that's annoying. Why is everything so different? All right, so we'll concatenate the base prompt and the completion function. Okay. Oh, but it's Oh, right. So this has to be. We don't have to call it get weather US. We can just call it get weather. There you go. Oops, but we have to have it be consistent there. All right, there we go. Same kind of odd answer. There we go. So here's the new prompt. Final output. Uh, Nothing. Uh, huh. Okay. Well, that's not working. Okay, so it wasn't a valid city name. Huh, it's still getting a different answer. So it must be that the um okay. Well, this seems to be going kind of wrong. Yeah, final answer should have been there, but so we learned how we can create agents from scratch using Python code, and we saw just how tedious that process can be. And for me, it didn't even work. Fortunately, many agent libraries simplify this work by handling much of the heavy lifting for you. Now we're ready to create our first real agent using the small agents library. All right. So in the last section, we learned how we can create agents from scratch using Python's code. And we saw just how tedious that process can be, and it didn't even work for me. Yeah, I'm not even going to save that. Fortunately, many agent libraries simplify this work by handling much of the heavy lifting for you. In this tutorial, you'll create your very first agent capable of performing actions such as image generation, web search, time zone checking, and more, and much more. You will also publish your agent on a Hugging Face space so you can share it with friends and colleagues. Let's get started. What is small agents? It's a secret agent like James Bond. It's got a gun there. To make this agent, we're going to use Small Agents, a library that provides a framework for developing your agents with ease. This lightweight library is designed for simplicity, but it abstracts away much of the complexity of building an agent, allowing you to focus on designing your agent's behavior. We're going to get deeper into small agents in the next unit. Meanwhile, you can also check this blog post or the library's repo in GitHub. Let's check the repo for small agents. And I'm going to star that repo. All right. In short, Small Agents is a library that focuses on code agent, a kind of agent that performs actions through code blocks and then observes results by executing the code. Here's an example of what we'll build. We provided our agent with an image generation tool and asked it to generate an image of a cat. The agent inside Small Agents is going to have the same behaviors as the custom one we built previously. It's going to think, act, and observe in a cycle until it reaches a final answer. Exciting, right? Yeah, it is. All right, so somebody's kid is in the background. So we generate an action, execute and observe the results. Then it will repeat the think, act, observe cycle to try again. Success. We created a cat agent. So next we will create a child care agent. I mean, continue with the tutorial. So let's build our agent. To start, duplicate this space. Okay. So thanks to a Miric for this template. So we got to duplicate this space. I don't know how to do that. So this is spaces. Let's click on that. Okay, so that takes us back to that. Let's click on this here. Um, so we can run locally, clone, add to collection. So we can duplicate this space. Let's go with that one. So, yep, so I'm now the owner. First agent template. Visibility, let's make it public so other people can see my work. And then we've got, okay, so we can either use free hardware or we can pay for more sophisticated hardware. We can get an NVIDIA A10G with 12 vCPU. That's pretty good. NVIDIA A10G. Here we go. Tech Power Up is my favorite place to go for this. So it looks like this would so compared to the latest and greatest, which is now a 5090, it is a the 5090 is only twice as good. So it's pretty solid, especially if you can get it for like it for me like the holy grail. Like I want to build a home lab, but at the same time, things are changing so fast. Like by the time you get your home lab up and running, like it's gonna be like if you had built a home lab with 4090s, which as of early like a week or a month ago would have been the absolute latest state of the art home lab. Overnight, your home lab would now be uh, not as capable as if someone uh, built it, a few months ago with the latest and greatest. So, it's a race that you can't win on your own. So going through and paying for GPU is probably a good idea if you want to do something serious. You've got to decide whether you want to build or buy. We read a whole chapter of that in my other series from this book. But buy is not necessarily a bad option. And look, the so you can get a massive massive hardware for 950 an hour. If you want to use a TPU, you can also use a GPU. The most expensive option they have is 2350 an hour. So you're paying it the same. You know, you might be able to find an actual human programmer that would be willing to accept that, especially kind of an entry level. So interesting. I'm going to go with the free. I'm going to duplicate the space. All right. So duplicating this space means creating a local copy on your own profile. Throughout this lesson, the only file you will need to modify is the currently incomplete app.py. So let's get that queued up if I can. Yep, so everything looks like it's done. So we'll get to that queued up. We'll go to Files. We'll go to app.py. There we go. And then I'll click on Edit, and we'll be modifying this file. You can see the original one in the template, which is good. So we'll keep that open as well, so that we can see the difference between my changes and what the original has. To find yours, go to your copy of the space and click the Files tab, and then on app.py in the directory listing. Let's break down the code together. The file begins with some simple but necessary Python library imports, of course, as always, typically. As outlined earlier, we will directly use the code agent class from small agents. So here it is. The tools. Now let's get into the tools. If you want a refresher about tools, don't hesitate to go back to the tools section of the course. So there, we can decorate it with the, yep, so with this. So I don't know where this is, this function, decorator function is defined. Oh, so it's imported from small agents. That comes, they give you that automatically. All right, so here's what you want to modify and fill in. All right, now let's get into the tools. If you want a refresher about tools, don't hesitate to go back to the tools section of the course. The tools are what we are encouraging you to build in this section. We give you two examples, a non-working dummy tool that you can modify, which is here, an actually working tool that gets the current time somewhere in the world. So I'll probably start with the second one, it'll probably be easier. To define your tool, it is important to, number one, provide input and output types for your function, like in get current time and time zone. So the time zone would be a string. So it would take in the time zone as a string, and then it would output it as a string. A well-formatted doc string. Small agents is expecting all arguments to have a textual description in the doc string. Okay, so all arguments to have a textual description. So that means, yeah, so like if you add arg1, you have to have something like this. You know what? I feel like this is really buried. Yeah, we're already almost an hour and a half in, and this is kind of the good stuff, actually fiddling around with the code. So I want to end this video here and then do this at a later time um, as a dedicated video for it. So that's going to be it for this video. Stay for the next one where we modify this code and just play around and have some fun. Um, and then read about the agent next.